All right, so get this. Have you ever seen those incredible auroras? The ones that just light up the night sky?
Oh, yeah, they're amazing.
Well, we're diving deep into the science behind those auroras today.
Sounds cool.
It is. And trust me, it's way more interesting than just pretty pictures. We've got some fascinating new research from NASA to unpack. It's from an experiment called KiNET-X.
Okay.
And get this, it involves barium explosions in space. Barium explosions.
Wow. That's pretty wild.
It is pretty wild. So before we get to the exploding barium, maybe you could give us a quick refresher on what causes auroras in the first place.
Sure.
I mean, we all know it has something to do with the sun and Earth's magnetic field, right?
Yeah. So it all starts with the sun. The sun's constantly spewing out this stream of charged particles, and it's called the solar wind. Now, when these particles reach Earth, they run into our planet's magnetic field, which acts like a shield and deflects most of them. But some of these charged particles, they manage to sneak in. They kind of spiral down towards the poles along the magnetic field lines.
Okay, so those particles are heading towards the poles. But how does that create those shimmering lights we see, those auroras?
Well, that's where things get really interesting. As these charged particles from the sun slam into the Earth's atmosphere, they collide with atoms of oxygen and nitrogen. And it's these collisions that excite the atoms, causing them to release energy in the form of light, and that light is what we see as the auroras.
So it's like kind of like a cosmic game of billiards with the sun's particles as the cue ball and Earth's atmosphere as the felt.
Yeah, that's a pretty good analogy.
So we got the basics down. Now let's talk about this KiNET-X experiment. What was NASA trying to figure out with this mission?
Okay, so while we understand the general idea behind auroras, the specifics of how electrons get accelerated to those high energies that create the auroral glow are still kind of a mystery. And that's where KiNET-X comes in.
Okay, so they weren't actually trying to create a giant artificial aurora in the sky?
No, that wasn't the goal. The KiNET-X mission was designed to replicate in a controlled way the conditions that lead to electron acceleration within auroras. And they had to launch it from Virginia within a very precise 9-day window in 2021 to make it happen.
So how did they go about replicating those conditions? This is where the barium bombs come in, right?
You got it. So KiNET-X released these 2 canisters of barium thermite high in the atmosphere, which created artificial plasma clouds.
Okay, hold on. Back up a sec. Why barium? What's so special about that?
Barium it's a really clever choice because it has a low ionization energy. That means it easily loses an electron when exposed to sunlight, becoming a positively charged ion. And that's key because it allows the barium to quickly turn into a plasma, which can then interact with Earth's magnetic field, much like the charged particles from the sun.
Ah, so the barium is like a stand-in for the solar wind, creating like a mini version of the conditions that lead to auroras.
Precisely. Now, remember those Alfvén waves we talked about earlier?
Yeah, those ripples in the sea of charged particles.
Exactly. Yep. They play a really crucial role in transferring energy within a plasma.
Okay.
And are thought to be key to accelerating electrons in auroras.
So how did the barium clouds help study these Alfvén waves?
Well, the interaction of those 2 barium clouds with the ambient plasma already present in the ionosphere triggered Alfvén waves. This allowed scientists to study them in a controlled environment.
So they essentially created like a mini aurora lab up in space. Did it work?
It did, and the results were really exciting.
I bet. But before you spill the beans, you mentioned this golden data point hidden within the experiment data. What's that all about?
Ah, yes, the golden data point. It's one of the most fascinating findings from KiNET-X, and it really highlights how this experiment helps us understand aurora formation. But let's dive into that in the next part of our deep dive.
Okay, you've got me hooked. What's this golden data point all about? And what does it tell us about how auroras form?
Well, as you know, one of the big questions about auroras is how electrons get accelerated to such high speeds, to create those brilliant displays. KiNET-X was designed to test the theory that Alfvén waves play a key role in this acceleration process.
Right, because those waves can transfer energy within the plasma, potentially giving those electrons a boost. But how did KiNET-X actually confirm this?
Well, the experiment measured the electric fields generated by that Alfvén wave, the one created by the barium clouds, And here's the big aha moment. The data clearly showed electric fields aligned parallel to Earth's magnetic field lines.
Okay, and why is that parallel alignment so important?
Because that's exactly the type of electric field needed to accelerate electrons along those magnetic field lines towards Earth's atmosphere. It's like those field lines become a superhighway for electrons, and the electric fields are pushing them along, giving them that extra energy.
So the barium clouds created Alfvén waves. The waves generated those electric fields, and those fields can accelerate electrons.
Got it.
But where does the golden data point fit into all of this?
That's the really cool part. Remember how the barium gets ionized? It essentially becomes part of the plasma. Well, within all that data, the scientists found this tiny beam of accelerated barium electrons heading towards Earth. They called it the golden data point because it provided direct evidence that the Alfvén wave was indeed accelerating electrons.
Wow, so they didn't just measure the electric fields, they actually detected those accelerated electrons themselves. That's incredible.
It's pretty amazing, right? And this golden data point, it wasn't just a fluke. It aligns perfectly with theoretical predictions, and it helps solidify our understanding of how those invisible electron beams, which ultimately create the auroras, come to be.
This is really blowing my mind. It's like we've gone from just watching those beautiful auroras in the sky to understanding the intricate physics happening at the atomic level. But this is just one experiment, right? There must be other research going on to study auroras.
Absolutely. KiNET-X was a crucial step. But it's just one piece of a much larger puzzle. There are tons of scientists around the world using different tools and techniques to unlock the secrets of auroras.
Like what? What other research is happening?
Well, one area that's particularly fascinating is the study of aurora substorms. You can think of them as these sudden bursts of activity that really intensify those auroral displays. They're driven by these complex interactions between the solar wind, Earth's magnetic field, and a region called the magnetotail.
Magnetotail. That sounds intense. What is that exactly?
Well, you can imagine that Earth's magnetic field is like a long flowing dress. The magnetotail is that trailing part of the dress that extends way out on the night side of Earth, sculpted by the constant pressure of the solar wind.
Okay, I think I'm picturing it. So how does this magnetotail relate to substorms and auroras?
Well, scientists are finding that during a substorm, this huge amount of energy that's stored in the magnetotail gets released, and a portion of it shoots back towards Earth. This energy release triggers this whole cascade of effects, including the acceleration of even more particles that create those intensified auroral displays that we call substorms.
So substorms are like auroras on steroids.
In a way, yeah, they're more dramatic, they're more dynamic, and they play a key role in transferring energy from the solar wind into Earth's magnetosphere and ionosphere.
That's pretty wild. And it makes sense because we've all heard about those incredible auroral displays that happen during solar storms, right? It's like the whole system's going into overdrive.
That's a great connection. When we talk about space weather and those potential impacts on our technology, understanding these substorms is crucial. By studying them, we're getting closer to predicting and mitigating the effects of these powerful events.
So it's not just about understanding, like, the beautiful light show. It's about protecting our satellites, our communication systems, and our power grids from these solar storms. It's amazing how something as seemingly ethereal as the auroras can have such a tangible impact on our lives.
Isn't it fascinating? And it underscores how important continued research into these phenomena is. We need to gather as much data as we can from as many sources as possible.
Speaking of sources, what other tools besides rocket experiments are scientists using to study auroras and substorms? I imagine telescopes must play a big role.
They certainly do. Ground-based observatories, equipped with these specialized cameras and instruments are constantly monitoring the skies, capturing those dynamic auroral displays. And these observations provide this valuable data about the aurora's shape, intensity, and movement.
That makes sense. It's like having a front row seat to the auroral show. But ground-based telescopes can only see so much, right?
That's where satellites come in. They give us that global perspective that we just can't get from the ground. Satellites like Themis, for example, are orbiting Earth, constantly monitoring the solar wind, mapping Earth's magnetic field, and tracking the flow of energy throughout the magnetosphere.
Wow. So we've got rockets gathering data up close, ground-based observatories watching from below, and satellites keeping an eye on the big picture from above. That's a pretty impressive network of tools.
It is. But there's another crucial tool in our arsenal that you haven't mentioned yet, computer models.
Oh, right. Simulations. I bet those are getting pretty sophisticated these days. How are scientists using them to study auroras?
Computer models are becoming increasingly powerful, allowing scientists to actually simulate the incredibly complex interactions between the solar wind, Earth's magnetic field, and the atmosphere.
So it's like a virtual laboratory for auroras and space weather.
Exactly. They're able to tweak different parameters in these simulations. They can run different scenarios and see how the auroral system responds.
So by combining all these tools, The rocket experiments like KiNET-X, the ground-based observations, the satellite data, and the computer models, scientists are gradually piecing together this, more complete picture of how auroras and substorms work, right?
Absolutely. And with each new discovery, we're gaining a deeper appreciation for the beauty, the complexity, and the sheer power of these phenomena. But, it's not just about understanding them for understanding's sake. There are some pretty big implications for us down here on Earth, too.
Okay, I'm all ears. How does understanding auroras and substorms help us in a practical way?
Well, as you mentioned earlier, intense space weather events like geomagnetic storms can disrupt our technology. These storms can interfere with radio communications, knock out GPS satellites, and even cause blackouts by inducing currents in power grids.
Oh, wow, that sounds pretty serious. So how does studying auroras help us protect ourselves from these space weather hazards?
By understanding the underlying physics of these events, the way energy is transferred from the sun to Earth, the role of the magnetotail, the dynamics of substorms, we can start to develop better forecasting models.
So it's like predicting the weather, but for space.
Exactly. And just like with weather forecasts, the more data we have, the better our predictions become.
So the more we understand about auroras, the better equipped we'll be to deal with the potential hazards of space weather.
Yeah.
That's a pretty powerful connection.
It really is. And it highlights how studying something as seemingly, abstract and distant as auroras can have such a direct impact on our lives here on Earth. But beyond the practical applications, there's something truly awe-inspiring about these phenomena, wouldn't you say?
Oh, I completely agree. Thinking about those invisible electron beams raining down on Earth's atmosphere, painting those incredible patterns of light across the sky, it's humbling.
It is. And it's a reminder that we're part of this vast interconnected system and that what happens in space can have such a profound effect on our planet and our lives.
It makes you want to look up at the night sky with a whole new perspective, doesn't it?
It certainly does. And who knows? Maybe one day you'll be lucky enough to witness an aurora for yourself.
I sure hope so.
Yeah.
It would be an incredible experience. But speaking of experiences, you mentioned earlier that the KiNET-X experiment involved releasing those canisters of barium thermite high in the atmosphere. What did that actually look like?
Ah, yes. The barium releases, well, those canisters didn't just explode randomly. They were carefully timed and positioned to create those two distinct plasma clouds.
And these clouds were visible from the ground.
Yeah.
Right. Did they look anything like the auroras themselves?
Not exactly. While the barium clouds did glow, they weren't the same shimmering, dancing curtains of light we see in auroras. Think of them more like colorful, expanding plumes. Imagine two puffs of vibrantly colored smoke high in the sky, gradually spreading and interacting with the ambient plasma.
Okay, so not quite the northern lights, but still a pretty spectacular sight, I imagine.
Oh, absolutely. And what's even more remarkable is that those colorful plumes, captured in images and videos, weren't just a visual spectacle. They were a tangible representation of the science at work, helping researchers visualize and analyze the complex processes unfolding high above Earth.
It's amazing how something so visually stunning can also be so scientifically significant.
It truly is. And it's a reminder that science isn't just about, cold hard facts and equations. It's also about wonder, exploration, and the thrill of discovery.
Well said. And I have to say, this deep dive into the science behind auroras has definitely sparked my sense of wonder.
I'm glad to hear it. But our auroral adventure isn't quite over yet. We've explored the science, the research, and the practical implications. But there's another fascinating aspect to these celestial displays that we haven't touched on yet. The human element.
You mean like how auroras have captivated people's imaginations throughout history?
Exactly. Long before we understood the science, people from all over the world have gazed up at those shimmering lights and woven stories, myths, and legends to explain their existence.
That sounds fascinating. I'd love to hear more about those stories. And I'm also curious to know if there are any ethical considerations when it comes to aurora research. Like, does launching rockets and releasing chemicals into the atmosphere have any environmental impact?
Those are both great questions. And they're perfect segues into the final part of our auroral deep dive.
So you were about to tell me about the stories people used to tell about auroras, before we knew the science behind them. I mean, can you imagine seeing those lights dancing in the sky and having no idea what they were?
Oh, I know. It must have been both awe-inspiring and maybe even a little bit terrifying.
Yeah.
Imagine, trying to explain those shimmering curtains of light without any concept of solar wind or magnetic fields or colliding atoms.
I bet it fueled some pretty wild imaginations. What kinds of stories did people come up with?
Well, the stories, they vary widely across different cultures and traditions. For example, many indigenous peoples of North America, they saw the auroras as spirits dancing in the sky. Often they were associated with their ancestors or animal spirits.
That's beautiful.
Hmm?
And it makes sense to connect those lights with the spirit world. Did other cultures have similar beliefs?
Some did, yeah. But others had very different interpretations. In Norse mythology, for instance, the auroras were thought to be reflections off the armor of the Valkyries, those mythical female figures who decided who lived and died in battle.
Whoa, that's intense. It's fascinating how these natural phenomena have been woven into so many different belief systems throughout history.
It is. And even today, with all our scientific knowledge, there's still something magical and mysterious about auroras, wouldn't you say?
Absolutely. It's like they bridge the gap between science and mythology, connecting us to both the rational and the imaginative parts of ourselves.
I love that way of putting it. It reminds me of this one time when I was doing field work in Alaska, studying auroras. I was out late one night with some colleagues, and we were just surrounded by these incredible swirling curtains of green and purple light. And as we're taking measurements and collecting data, this group of tourists came up to us, and they were just awestruck. They started asking all sorts of questions, not just about the science, but also about the myths and the legends.
That's a great story. It shows how auroras can spark curiosity and wonder in everyone, regardless of their background or their level of scientific knowledge.
Exactly. And that brings us to your other question about the ethical considerations of aurora research.
Right. I was curious about the environmental impact of those rocket experiments, like KiNET-X.
Yeah.
I mean, releasing chemicals into the atmosphere, even if it's for scientific purposes, has to have some kind of effect, right?
Yeah, that's a very valid concern. And thankfully, scientists are very aware of the potential impacts of their research, and they take steps to minimize any negative effects.
So what kind of precautions are taken with these rocket launches?
Well, first of all, the amount of barium released in experiments like KiNET-X is incredibly small compared to the vastness of the atmosphere.
Okay, that makes sense. It's not like they're setting off giant barium bombs up there.
Right, exactly. And the barium itself isn't particularly toxic. It's actually used in some medical procedures.
Really? That's surprising.
Yeah, it is. But of course, any release of material into the atmosphere needs to be carefully considered. That's why scientists conduct these thorough environmental impact assessments before these experiments, modeling the dispersal of the barium and evaluating any potential risks.
So they're basically doing their due diligence to ensure that the benefits of the research outweigh any potential drawbacks.
Exactly. And it's worth noting that the insights gained from these experiments can actually help us better understand and protect our environment.
How so?
Well, remember how we talked about the connection between auroras and space weather? Data we collect from experiments like KiNET-X can help us improve our space weather forecasting models.
Right. And better forecasting means we can better prepare for those solar storms that can disrupt our technology and even pose risks to astronauts in space.
Precisely. So in a way, these aurora studies are contributing to our overall understanding of the Earth system and helping us protect our planet and ourselves from potential hazards.
Wow, that's a pretty incredible ripple effect. It's amazing to think that something as seemingly distant and ethereal as auroras can have such a tangible impact on our lives and our understanding of the universe.
It is. It really is. And it highlights the interconnectedness of everything, from the tiniest particles in the atmosphere to the vast reaches of space.
Well, I have to say, this deep dive into auroras has been a truly enlightening experience. We've gone from the basic science to the latest research, explored ancient myths and modern technological implications, and even touched on the ethical considerations of scientific exploration. It's been quite a journey.
It really has, and I'm so glad we could share it with you.
If you're anything like me, you're probably looking at the night sky with a whole new perspective now, and maybe even hoping to catch a glimpse of those shimmering lights for yourself one day.
I hope you do. It's an experience that will stay with you forever.
Well, on that note of cosmic wonder, I think it's time to wrap up our auroral adventure for today.
It's been a pleasure diving deep with you.
We hope you enjoyed this journey from those mesmerizing visual displays down to the intricate physics of Alfvén waves and electron acceleration. We hope you learned something new, sparked your curiosity, and maybe even gained a deeper appreciation for the beauty and complexity of the universe we inhabit.
And if you're eager to, delve even deeper into this topic, we've got some fantastic resources linked in the show notes, including links to NASA's website, where you can learn more about the KiNET-X mission and see some incredible images of those barium releases.
So keep those minds curious, keep those eyes on the sky, and never stop exploring. Until next time, thanks for joining us on the Deep Dive.